Hello, good morning, everybody. I'm really impressed with your presence. I had to be here, you didn't, so thank you for this. And today I will talk to you about TensorFlow and how I compacted it in 3 sentences. As you can imagine, if you want to really know well TensorFlow, you probably need more than an hour and probably more than 3 sentences. But those 3 sentences I chose for you, I think they are a good start to play with it, to understand what it is not, and hopefully give you a head start when you want to dig deeper. Just out of the curiosity, who here have ever worked with TensorFlow or touched TensorFlow? Great. Who has ever worked with deep learning, AI, machine learning? Okay, cool. Who has come here because this big hype of machine learning, AI, and all those robots? Yes. Yes. So we have quite a diverse audience here. And as I said, I'll show you some stuff that are introductory to TensorFlow, but I will go deeper, and I will show you how I'll go deeper in a second. So who am I to talk to you about TensorFlow? I used to be a programmer for years, but I did my master's degree in machine learning, although back then we didn't call it machine learning. We called it maybe data mining. We called it AI. And I was dealing with fuzzy rules, with genetic algorithms, and there was this niche thing that my mentor said, don't go there. And those were neural networks. And I should be mad at my mentors now, because as you know, it's a big thing at the moment, but I will explain to you in a second why I'm not. So what am I going to talk to you today about? First, we'll talk a little bit what's deep learning. And as you may know, everyone has their own definition, and there are a lot of articles, headlines, blogs, courses, and etc., universities even, that talk about deep learning and AI. And then I will introduce you with the NIST data set, and then I will use this data set in my 6 demos, if the time and Australian network will allow us to do. But I have a good news for you. All those demos are available for you on the platform called Katacoda. It's not just that you will have the code, you will have the whole environment to run it. Just basically do whatever I will be showing you today. And go into more details. You can spend more time on those demos than I have within this hour. So what's deep learning? Who can tell me what's deep learning? Subset of machine learning. Sure. Anyone else? It involves neural networks. Yes, why deep? Multiple layers. So the official definition is if we have more than 2 hidden layers. And for those of you that don't know, I'll explain what hidden layers is in a second. Then we call it deep learning. And my favorite definition is matrix multiplication. Because everything that is mathematically down deep in those neural networks, basically you take one matrix, another matrix, you multiply them, you add them together, and you get miracles. And that's my point, actually. We are now, at the moment, living in a future when technology is almost indistinguishable from magic. Yeah, read this guy's t-shirt, it's also very funny. So when I'm thinking about deep learning, when I'm thinking of AI, this is the technology that actually made it possible. That when I was watching the movie of, I don't know, Harry Potter, and I had this feeling, because I'm a programmer, so I was biased, that Hermione is this brilliant hacker. She knew all the spells / commands, right? And she could just achieve everything she wanted because she was a very good student, and she knew all of this. And whenever I think of stuff like this, I cannot not think of technology and how it is actually magical. So what are those neural networks? So natural neural networks, the ones that we have in our brains, of course have neurons. Neurons are those structures that look kind of like this, There are connections between them. There are some signals passing from one neuron to the other. And basically, this is the moment when the analogy stops, when we talked about artificial neural networks. Because artificial neural networks are just numbers, are just weights. So if you look at this very simple neural network, we have 3 layers here. Input layer, it's basically what we want to classify, find out, what we feed our network with. There is an output layer that has different sizes, depending on our problem. If we're thinking about classification problem and we have 3 classes to predict, we'll have 3 output neurons. And then we have this hidden layer, which is not really hidden. You can access it quite easily. But some PR people think of it as a hidden layer. Maybe back in the days, it was actually hidden. So what is happening inside all those neurons? As you can see, this is an example of so-called dense layer. So every neuron has the connection to every neuron from the layer before. And what is happening? It takes the input, it multiplies it with weights, then adds it, and then put it through some activational function. And if you know a little bit about linear algebra, you know this is basically what matrix multiplication is. If you treat those inputs as matrix, if you treat the weights as matrix, this is what you get. This is how you multiply matrices. Activation function plays different role in depending where we are, which layer are we talking about. But it's basically some function that you take your values, put it through, nothing magical with it. And this aggregation equation is all over the places, and it can actually do miracles. So why am I not angry at my mentor when I was doing my PhD? Because neural networks were there forever. Soon there will be like 100 years when first neural networks were thought. So they were basically since the actual computers were invented. And the real hype was around 2008, 2009. And well, seriously, no one actually predicted it. And it has happened to be a big thing at the moment. So what happened? What changed? Why now neural networks are such a big thing? Machines are stronger.
Bigger data sets.
We actually have big data, right, at the moment. Anything else? GPUs, yes, all those things. We have cloud. Everything is quite cheap, so everyone can access everything. And we have libraries like TensorFlow. TensorFlow is not the only one. It just happens to be the most popular at the moment. But all those efforts of democratizing AI, of democratizing neural networks, are actually paying off. And there is another reason. Neural networks happen to solve the biggest AI problem there is. Who can tell me the biggest AI problem there was, because they solved it? It's distinguishing cats from dogs, if you didn't know. For years, we didn't know how to explain to the computer how to distinguish and actually recognize it on a picture. And now we can, all because of those multiplications and adding stuff. Let's start with my first sentence. My first sentence is build a computational graph. So for those of you who know TensorFlow, this is your first, when you first encounter TensorFlow, they tell you to build a graph. What is it? It's basically something very simple, like you can see at the top. You have some operations, you have some inputs, and those operations are taking those inputs and, well, perform those calculations and have some outputs. And those inputs, if they are not the output of another operation, they are called tensor, hence TensorFlow. What are tensors? Tensors are basically multidimensional arrays. And thank God we have computers, because our human beings, we cannot really imagine more than 3 dimensions. If you can, any of you, I want to offend you, but most of us, we cannot. And machines are great because they don't have to imagine anything. They just take multidimensional arrays and perform calculations. And linear algebra works very well on any dimension you basically can imagine. Simple examples, of course, will play with your imagination, so start with 2- and 3-dimensional stuff. So how to build this computational graph? First of all, you're just saying which calculations, which inputs, which output are you expecting. And then there is this thing that is called deferred execution. So the fact that you've built this recipe doesn't mean it's been run. So first you're building it, then you're starting a session, and then you can run basically any bit of it. You don't have to run the whole thing. You can just run this adding thing. And there is a tool called TensorBoard that is also available for users of TensorFlow. And you can build very complicated stuff. You can drill down and see how does it work. And it has very nice visualization because, you know, the code is great and we all love to code, but if you're building complex stuff, you sometimes, I do this very often, used to do this very often before this tool, I had to draw my calculation draft to, you know, not get crazy. So let's see how you can build computational graph in TensorFlow. So if you go to this course, I have 6 demos for you, and I will just start the first one. So as you can see, this is all in a browser. You can access it for free, and you can just use it. Basically, what is on those guided lines here is a little bit what I'm saying at the moment, and a little bit more because I added more content. This is the bash. It has nothing to do with Python or TensorFlow. First, I just want to go in a bash of Python, and then I can start using TensorFlow. So to use TensorFlow, I need to import it. I think I can go with presentation mode, yeah. And to start working with TensorFlow, we'll just build very simple computational graph. We'll take 2 constances, and we'll add them. And to build constants, you just use constant function in TensorFlow. And you need to remember that because you just defined it, it's still part of the computational graph, doesn't mean they are actually holding any values yet, because we didn't run this computational graph. So if I print it, I'm not getting values 2 and 5, right? I'm getting information that I have 2 tensors of those types and of this kind of a shape, etc. So let's start a session, and this is how you run your computational graph, and then use session run. As you can see, I've used session run, put my inputs there, and now, because now I run it, now I actually put all of this through calculations, I have my values 2 and 5. And that's basically the whole idea of computational graph, that it's a very simple example. So let's try something more complicated. Well, let's build this adding example. So I'm using add function here for my add node. And let's print it. Let's print first the node and then running this node. So first we are expecting there will be a tensor displayed, and second, the output of adding 2 and 5. Now maybe I'll go out of presentation mode. Okay, sorry. I think it's the network problems. So you can see there is a tensor printed, and then there is 7 printed at the end. Let's start with that. Okay, constances are not very, they're not very interesting, but they're useful because in many of our calculations we need them. What is more interesting are placeholders. And I don't have a better definition, but placeholder is a placeholder. So whenever you're building your graph, you're saying, well, this is when I expect some input to my further calculations. So you're building a graph and saying, I will be expecting a float number there. And then I will be expecting a float number there. And at the moment of performing session run, you need to feed your graph with the actual values. And I will show you how to do it. So let's create those placeholders and then create the node that is adding them. And you can see that I used plus instead of TensorFlow add because that's nicer and what we are used to, and it works also. So now we want to run our session with a specific value. So you can see I'm saying run my session with this adding node and feed it with 2 and a 5 for placeholder 1 and placeholder 2. Then feed it with 1.2, 3.5, and then feed it with 2 arrays, 1, 2, and 5, 8. And only the recipe is the same because I'm feeding it with different values. And there you go. As expected, we have values 7, 4.7, and 6 and 10 because arrays can also be added together. So that was easy. The part that is not that easy are variables. So variables are kind of like constants, but they can change their values. So you have to initialize it with some values, as you can see. I'll show you that here. So you have to initialize them with some values. So I'm initializing my A with value 1 and my B with value -2. But then, when you're performing your calculations, you can change its value. And if you think about machine learning process, this is what machine learning process is doing. There are always some variables, there are always some parameters, coefficients, that you want to adjust for your loss function to be minimized. And I'll show you a very simple example, not really connected to machine learning at the moment, but maybe a little bit later, how to do it. So let's think of very simple linear model, A times X plus B. So we will have our 2 placeholders, X and Y, and we'll feed our algorithm with the proper values, and we'll try to adjust A and B, which will be our variables, to fit the perfect line for our points. So I'm defining my 2 variables, and I'm defining my linear model. And because we are using variables, you need to do some trick. There is this one trick. You need to initialize all those variables before you're performing any of your calculations. So I'm initializing all the variables. This is just the step you need to always do. So what I am now doing is nothing different than what we did with placeholders. I want to run my linear model with X values from 0 to 5. So we have our preliminary values for A and B, and we're feeding it with X. So we know the perfect points of Y would be those. So let's start. Let's try to I'll make it a little bit bigger. We started with the green line, and we want to adjust it to fit the blue line. So that's basically the goal if you want to fit the linear model. And of course, normally you're using some kind of optimizers. I just know the values, so I will just go straight to the point and just change those values. But first, I'm defining a loss function. So basically, I'm taking a differences from my points to the line, and I'm putting a square on it, and then I sum it up. That's a very popular way of having a loss function. Then I'm feeding my algorithm with X and Y values, and I'm printing the loss function for this, as you can see, green line. So what I did was I'm taking this point, I'm taking the difference, taking this point, taking the difference, and adding all those squares of those differences. And my loss is pretty high. I would like it to be 0. In this case, I know it can be 0 because I know the actual values. Normally, it won't ever be 0 because real data are not allowing us to be 0. And I know the exact values, so I would just change my variables, and this is where tf assign comes in. You can change your a and b, then you run it, and then I'm printing my loss again. And my loss is now 0, but this is the only time when you get the loss 0. In the real world, it will never happen. So let's go back to my slides, and let's go through more interesting actual machine learning examples. So we'll go through classification task that is hello world task for deep learning, which is classification of handwritten digits. So this is a very well-known data set, and you can go there, download it, play with it yourself. What is funny, this data set works very well with a very simple k-nearest neighbors algorithm. We don't really need deep learning for it, but it is, those are images, and it's very good exercise to do it on this data set, and neural networks are trained very quickly on it, so I encourage you to go through this exercise. So how do I approach it, or how TensorFlow as default is approaching it? Those images are 28 by 28 pixels, so TensorFlow is flattening them. So our input layer will have 784 input neurons. Then the training process is a little bit different than a classical training process, because you can probably never get an example online about deep learning neural networks that is trained on the whole training set. It always works in batches. First of all, it's quicker this way, because you don't feed in every step of your algorithm, you don't feed it with the whole thing. If you think that this data set has 20,000 of images, it's quite a lot. Every step would take ages. And second of all, it's kind of it's reducing overfitting. Overfitting is the thing when the machine learning algorithm is learning by examples by heart. So almost never you will get an example online about TensorFlow or deep learning that is not taking batches into account. And once you have your trained model, what you can do, this is what actually we will build in the second demo. We have our input layer, we have our output layer, which has 10 neurons, because we have 10 labels, we have 10 digits. And once this whole thing is trained, which means all of the weights and all of the biases are adjusted, we can feed it with the new example, and hopefully we're getting the label 9 for this specific example. So let's do it. Let's build our computational graph for the machine learning process. I will just reset it to default. So remember what we want to do. We just want to build one output layer that has 10 neurons. And all I just said is here, so you can then go through this. First, what I want to do is I want to import all the TensorFlow stuff, and I want to read my data set. And TensorFlow makes it very easy because it's a hello world data set, so it has capabilities of just reading it, downloading and reading it, so you don't have to do it yourself. Second thing we want to do, I want to set up some variables, some numbers, so I'm not using numbers in my code, don't like to do it. Our image size is 28, as I said. Label size, we have 10 labels. Learning rate is 0.05. We will train our neural networks in 1,000 steps, and batch size will be 100, which is pretty small batch if you think of 20,000 examples in your training data set. So let's train our stuff. So first, I need some placeholders. And this is where you will very often get stuff in examples or in real life. You get your training data as a placeholder, and you say, when you're training it, or then when you're evaluating it, use this data set, use these images. And then you're saying, but those are the labels. So for example, when we are thinking of our training process, those are the true values. Adjust the coefficients so they fit those real values the best way. But you can use those labels also when you're evaluating later your algorithm. I will show you that in a second. And then we need our variables. Now, this is the tricky moment. So we have variables for the weights, and we have variables for the biases. And then we are creating the output layer that is multiplying our input data with our weights and adding the bias. So I have my variables. I just initialized them in a different way. I didn't actually put numbers there. I just said use normal distribution for weights and use constant value 0.1 for biases. And my output layer is just multiplication. You cannot actually do stuff like x time w, because this will multiply your matrices, like literally take piece by piece and multiply it. So it's not matrix multiplication. That's why you need to use this function. What else I want to do is define my loss function. So my loss function is reduced mean with softmax cross entropy with logits, and I'm not going to go into details. It's all explained in the scenario. You can go through this later. It basically means adjust it to the true values of the labels I will provide you with. And then I'm saying training step, every one of the 1,000 of the steps, use gradient descent optimizer with this learning rate and minimize my loss. So I really like this level of abstraction, but if you don't know much about what's underneath, you can get pretty lost. And this is kind of a point I'm trying to make here. TensorFlow is one of the tools that you can reach, use for free. It's open source, etc. But if you don't know what's underneath, you will just get some values, and you won't be able to well, basically judge if this is an okay value, if this is a meaningful value, will this bring anything to your business? But basically what we are doing in this line is, this is my training step, use this optimizer to minimize my loss function. And then I want to build another node that I call accuracy, not just I call. But basically I want to build a node that is checking how many times I was right. What's the rate of me being right, or what's the rate of my neural network being right? So it's taking the number of times the network was right when classifying images and dividing by the number of examples. And there is this part when we need to start the session and initialize all the variables, and then start our training process. So what I'm saying is, you know me this data set, get me a batch in every step, and then feed my algorithm with input batch and input labels. So this is where placeholders are being filled in. You're getting your input data, you're getting your labels, and you're feeding it with the training algorithm. And what I also want to do, I want to see how my algorithm is performing every 100 steps. So, sorry. So I'm evaluating. This is another way how you can run the session, an actual calculation. Instead of doing session run, you can do eval. And remember this accuracy node we defined before? I'm saying take my batch and see what's the accuracy at the moment of my neural network on this specific batch. And then just display it. And the last thing I want to do, I want to evaluate my model once it's trained. So you can see here, we're training our neural network, and after those 1,000 steps, we have ready-to-use model. Then we can classify new examples. And I'm taking those new examples from a NIST test data set. And I'm just running all this accuracy thing on the examples that weren't available during the training phase. Okay, we are now ready to run it. So first thing, sometimes takes time, but you can see it's a very simple network, so it worked very quickly. And I will show you more advanced examples in a second. But you can see that first it read all the data set. I can even see the folder here with this data set. Then it went every 100 steps and calculated accuracy on the current batch. And at the end, we just checked how does it perform on the new examples. And you can see that you can see kind of a progress, but it's not very consistent because it's only being trained on few batches and it's only calculating the accuracy of the specific batch. So that was building a computational graph. Very powerful tool, not always needed. And I will show you that in my second statement. TensorFlow is giving you different levels of abstractions. So you need to choose your level. You need to choose how are you comfortable with all those details, with all those variables, with all those biases. Do you actually want to adjust those variables? Maybe you just want to use something that is out of the box, an algorithm, and say, fit it, train it. And on the high level, when you think very, very high level of machine learning, deep learning is no different process, is you get the data, you need to prepare them and clean them. Don't be fooled, this part is taking up to 90% of your time when you're working as a data scientist. Then you're splitting the data or reading the data from different sources, so you have training data and test data, which we did for the previous example. And then there is this magic thing, fitting the coefficients. Once you have a trained model, you can evaluate it. So maybe TensorFlow will give me this high-level API that I just have my data, I can just fit it, evaluate. Flow, but you know some stuff about machine learning. Maybe this is the moment when you can start approaching TensorFlow. And I will show you in a second that there is no computational graph at this level of abstraction. This API is just doing it under the covers, so you don't have to actually build it yourself. So let's build a little bit more complex neural network. So remember, input layer, output layer, and we have a hidden layer now. So this hidden layer will have weights and biases in the same computational model as our output layer had before. They will be just different, and they will have different sizes because now this input layer is connected, hidden layer is connected with input layer, and output layer now needs to be connected to the hidden layer. So what we want to do is to use some model that will be this neural network with the hidden layer, fit it, evaluate it, maybe predict new things. So estimators. I will use, and there are different estimators. You can use like linear classifier. I will use DNN classifier, which goes for deep neural network classifier. And it also is building dense neural network, and this is what we will use for the same example. So let's open the code, and I will make it a little bit bigger. So I have my image size 28. Label size 10, and another variable I put here is hidden size. So the hidden layer will have 1024 neurons. That's basically it. I'm reading the data the same way I was reading it before, with one difference. There won't be one hot vector. There will be actual integers that are representing our labels. This is some function that is helpful, help function, and yeah, this is basically how you're defining your network. So let's go through it. DNN classifier, deep neural network classifier, because we'll be classifying stuff. We have feature columns, which I basically set up dimension image size times image size because we have 28 by 28. Hidden units, we only have one hidden layer, but if you want more hidden layers, just put anything you want here. It will just create another layer. We just want one. We have label size, we have 10 labels, and I'm using Adam optimizer, not gradient descent this time. So it's very simple. I'm just getting my inputs and saying, you know, classifier, fit it. Those features with those labels using batch size of 100 and 1,000 steps. Basically repeating what I had to do in several lines of code before, now in one line, with more complex neural network. And then I'm saying, get me the test data, and you know, classifier, once you're fitted, evaluate it. Evaluate it on the test data. And I have my accuracy. And then, once I have my accuracy, I'm saying, well, take another like 10 example from validation set and try to predict it. So yeah, I'll just run it now. It will take some time because it now takes time to fit it. The one output layer was very quick. When we added another layer, it needs to adjust coefficients, but yeah, you can see it's still pretty quick. And you see that test accuracy now, 97. It was 89 or something before, just because we added another layer. And those are predicted labels, and if you compare them with the actual values, at least for those 10 examples, it looks like it's performing pretty well. So this is a very high-level example. And yeah, if you just want to enter TensorFlow, start from it. Maybe not even from neural networks. Start from linear models. Start from k-means if you're doing clustering, etc. So, what if we want to do something more complex? We need to go into details. We need to build our networks, shape our networks ourselves. So, convolutional neural networks are the type of network, are the type of the layer in our neural network that work very well, happens to work very well on images, because it's taking into account and only performing calculations once once at the time on this 2D or 3D pieces of our input. So imagine we have the image, we have this square that is going through all of this image and performing the calculations. It's still matrix multiplication, don't get me wrong. It's just we're saving some space because we have much smaller kernel, much less of our weights and biases. And another thing is, if we're working with images and we're flattening our files, we're losing what are the stuff near each other. Once we have kernel like this, once we have convolution, and we are capturing stuff that are nearer to each other. It proved to be very, very effective. Another thing, another layer, although I don't call it a layer, is a polling layer. So after you're doing convolution, usually after you're doing convolution, you're doing something that is called polling. And again, there is this square that is going through your layer and trying to get either an average value or the maximum value or minimum value. Average and maximum are the most popular. So let's build a network that is very complex now. We have two convolutional layers. We have our hidden layer. And we can then put some dropped out at the end. We'll see. So one problem with, well, maybe not a problem. One different approach we need to do is we cannot work on the flattened file. We need to reshape it to be an image again, because that's how convolutional layer works. So let's see how we can use what we know about variables, about weights and biases to build such a complicated network. And we'll be using TensorFlow NN, which is a short for neural network, namespace. I'll go straight to the convolutional bit, and let's see how does it work. I've put all the training into separate files, so don't be confused. I will just focus on how to build the graph with all those layers. So we have convolutional layer, max polling, convolutional layer, max polling. Then we need to flatten our polling layer, and then we have hidden layer, and then we have output layer, a lot of layers. Placeholders are basically the same. What we need to do is reshaping our image from the flat one to 2D now. And let's build our convolutional layer. What we first need is weights and biases. Nothing different than from hidden dense layer. Then we're using a function that is called convolutional 2D. And not to go to many details, you really should understand what's underneath. First, I'm feeding it with those images. Then I'm saying use those weights and use those biases. And then I'm using strides, and then I'm using padding. So, and this is the bias here. Then I'm using polling layer. So I'm using max polling layer. And this is the moment when you're thinking like k-sides, strides, etc. And I really encourage you. It's the thing that could take me the whole hour to actually go. How does it work and how to adjust those parameters? Trust me on that this will work. But experiment, and this is why Katakoda is right there for you to see and try and fail and succeed. So this is our convolutional layer. And we have to do everything again for the second one. So we have weights, biases, convolutional polling layer, and at the end we have to flatten it. So again, flattening it. And then we have our hidden layer, weights, biases, hidden layer, and then I even added another layer, so-called dropout. Ask me later if you're interested what dropout is. And then I have weights and biases for our output layer, and I'm filling this dropout layer with output layer. So we have 5 to 7 layers, depending how do you feel about naming them layers. I'm very conservative. I just think the layer is the one that is holding the weights. So for me, we have 4 layers only. But even TensorFlow is not agreeing with me because it's calling them a layer. So let's try to run it. And this will take time, so I'm not going to go through the end, because we'll see this at the end. What I wanted to tell you is we went through very high-level machine learning, fitting, evaluating, predicting, to building our neural network from scratch. Maybe there is this intermediate ground, and there is. Maybe I don't have to think about all those variables, all those biases. Maybe I don't have to. Maybe I can do less work. I just want convolutional layer. That's it. I just want a dense layer, and that's it. And there is a middle ground. So you can see this 6, still 7 layers. It's the training is getting much longer because we have so many coefficients to adjust. So let me go to another demo that is taking, instead of TensorFlow and N, it's using TensorFlow layers. And this is the level of abstraction, some kind of a between. There are a lot of different levels of abstraction. I'm just showing you a few of them. Let's see the 2 convolutional layer. I think this will be next one. Yeah. So basically, the same network we're building, just be much easier. Placeholders, reshaping, same old, but I only have use convolutional layer and use it with those images. I need still some parameters, of course, and then instead of wrapping it with my ReLU activation function like I did here, you could see it right here. I was wrapping convolutional with ReLU. I'm just saying, you're a layer, you know what to do. Use this activation function when you're done with your work. So in this one line, in this one function, not just one line, one function, I just defined my convolutional layer. Then the polling layer. And the same for the second part. Instead of having a lot of deep calculations and at least two of the variables being defined, I only have one line, not just one line, just one function that I'm using. And then there is the same thing for the dense layer. I don't actually have to define my variables. I have a dense layer, and I'm just saying, take this as inputs, use this size, and use this activation function. And again, this dense layer doesn't have to be wrapped in the activation function. Output is as simple as this, but I'm not using activation function. So if you want to go in and try to tweak all those stuff, this scenario actually walks you through from one layer to all of them, so you can see how does it work, and you can compare how long the training is taking, because it is taking longer. As you can see, you can go back here. Yeah, finally it ended training, and now it's evaluating, so we have 97.15. So let me go back. We went through different levels of abstraction, and as I said, I didn't exhaust the whole list. There are a lot of stuff. There is Keras level, where you can basically choose your own deep learning library. So you're using very high-level API and saying use TensorFlow underneath, use Theano underneath, use Coffee underneath. And different level abstractions when you're working in TensorFlow and building your networks. Going to the third and the last sentence is work with the communities. And by communities, I understand everything from open source, from the support, from all of the people that are working, contributing to make this product better and better. TensorFlow is open source, as we all know, and this is an actual open source project, one of the few that got popular and that are actually working, that people from Google are working on, and it comes with all the flavors, all the great things, and also a lot of stuff that are not that great, which, in my opinion, it's not just TensorFlow, it's just every project, not just open source project, every project, is the documentation. Examples, tutorials that are there. And this is great, we have so many tutorials. Even getting started has over the 10. You have programmer's guides, you have APIs descriptions, you have, there is this thing, deploy, and there are extend, they're also having tutorials and the examples. And if you go to the GitHub repository, you have all the code that is there. The problem is, TensorFlow is releasing new versions, and documentation is not being updated. And it is going to be updated. It's just, it's more important to build new stuff than document them. And that's why we are working in Katacoda with TensorFlow team at the moment to tackle this problem. It's not maybe like a problem that we cannot live with it, because we've been living with this problem of every project, of course. But if you're thinking of getting an example from one of those tutorials, and they wrote it in a previous version, you very often don't have even information which version was it. And you're trying to run it, you get some warnings, sometimes errors, and there's nothing in between. What tools like Katacoda give you is the actual version you're working with, the code that is working with that version. The version changes, the environment stays the same. If you want to change it, if you want to upgrade it, you know which version was it. But there are a lot of great things, and I would say even another level of abstraction. We've built a MNIST neural network that was doing the classification problem for those specific images. But if you want, for example, translation, this is the example of the translation, there is a model somewhere there in the GitHub repository for those people who built the whole network, trained it, and serialized it. And it's somewhere there. You can just download it, build your model, use this Python script, and just translate stuff. This is very, very powerful thing. But for me, it's still like it needs one another step, or even another step. And what do I mean by that is, I will show you the example. Have you heard of ImageNet? No. ImageNet is this database of images that people went through the exercise to label them. And if you're building a neural network deep learning, machine learning algorithm for image recognition, this is the database you probably will tackle and try how your algorithm is performing. And there is this architecture called Inception v3. I'll show you this architecture in a second so you'll understand why Inception. And this code and this model is in GitHub repository. So you can just take it, use this model, and classify new examples. Just put some image there and classify it. It's just, we have Docker nowadays, right? I don't want to take this whole repository, build the thing. I want to just have a process that will run, take it, and serve me. And there are some attempts in the internet, but I think they are working with the previous version of TensorFlow. So if you follow the instructions, you can kind of figure out how to build this Docker image. But now you don't have to, because I will show you that image on Katacoda. This is, by the way, the image v3 kind of an architecture. Pretty complex, right? So good job, TensorFlow people, that you actually built it, trained it, and just gave us to work on. So the last demo I'm going to show you is using ImageNet, and it's using Inception and Docker. So Inception, if you can see this, architecture, now you cannot see it very clearly. It has like stuff inside. That's why Inception. So Katacoda built an image to serve Inception, TensorFlow Inception server. So we will run the server and we'll query it against few new images and check how does it perform, which labels it will give us. This image, if you want to use it at home, not on Katacoda, is also available publicly. So if you have Docker, if you just use what I'm using, it will work. We'll just download this image. So what I'm going to do, I'm just running the server, and I'm using this image, and then I'm running the command to set up the server inside and to serve me with capabilities of querying it. And Docker PS. Oh, Docker PS. Yeah, it's running. So what I want to do now, I want to go inside the server, and I'm in a bash at the moment. And then I want to classify those 3 pretty pictures. I was really, really curious what it will come up with. It was quite disappointing, you will see. So first, I'm just downloading it into this server, because they are not there. I just want them to be there. And then there is this very nice query. Just use Inception client on the server and use this cat image. And let's see what it comes up with. So if you go like up here, we can see this network clearly needs some training because it's obviously a grumpy cat. It's not that great with the puppy. I mean, with the puppy itself, it's okay, but it recognized a tennis ball. It's a red ball, it's not a tennis ball, right? I was the most disappointed with the dog. Dingo, Chihuahua, come on. Okay, that's it. That's the community work I was going to show you. And I think TensorFlow is going there. There is a lot of support in different ways. Like when you think of how many clouds are now supporting GPUs and even specifically configured machine to run TensorFlow, you can see how big it is, if you didn't know that before, of course. Is TensorFlow the best deep learning library? I would argue, but I would also say it's so massively supported by community that there is a big chance it will become the best one. At least the best one for us, regular people, that is not hidden in some big corporations inside, because there are also libraries that companies are using internally. So to finish this, I'll just summarize it. We started with the deep learning, and hopefully I convinced you about my definition of matrix multiplication, because it's just all over the places. And you really, really, I really couldn't believe at first, back in the days, years back, how powerful it is. Just simple adding and multiplying. Of course, there is some linear algebra there, and of course we have a lot of calculus inside to train it, but it's still very powerful and it still goes back to this multiplying and adding. Then we went through the 3 sentences, and I think this is a very good starting point if you want to enter the TensorFlow. Build a computational graph, use your level of abstraction, and work with the communities. And the point I'm trying to make is, especially with the second sentence, level of abstraction can be a bliss, because you don't have to deal with so many details. But it also comes with the price. You need to know about those details to use this proper level of abstraction. So with that, I would like to thank you, and go to Katacoda and have a fun.